Good morning, good afternoon, and good evening, and welcome to the Friday talk show with Global Electronics. And this is your host, Rajiv Kulkarni. The time is Central Standard Time of US. It's 6 minutes past 8 o'clock. Today we are a little bit delayed because we are trying to fix some technical glitches that we had last show, and hopefully we are going to rock today's show with our esteemed guest that he did present on a topic which we will discuss this very shortly. But before that, I just want to let you all know that I want to thank you all for supporting the channel and viewing our weekly broadcast that we do. Basic purpose of this Global Electronics Friday talk show is to help the electronics manufacturing community with the vast technology wealth that we have from various industry experts. They have worked in the field of electronics, whether it can be in design, whether it can be in product management, whether it can be in the purchasing or the process engineering or any field that you can consider in the electronics manufacturing sector. So we are going to discuss with them about the various topics that is being used in the electronics manufacturing, and so that wealth of knowledge can be shared with you all people out there who are in the business of electronics manufacturing. My name is Rajiv Kulkarni, and I'm based here in Dallas, Texas. And I've been in the industry for the last 30 plus years in the electronics manufacturing. And this is one of the reasons also that I want to give back to the electronics community that we have been serving for the last so many decades. So, ladies and gentlemen, let's welcome our esteemed guests for today. The topic of the talk show is 2.5D Heterogeneous Chiplet Packaging Challenge. That is episode number 2. Ladies and gentlemen, let's welcome our esteemed guests for today. The topic of the talk show is 2.5D Heterogeneous Chiplet Packaging Challenge. That is episode number 2. Let's welcome our esteemed guests for today. The topic of the talk show is 2.5D Heterogeneous Chiplet Packaging Challenge. That is episode number 1. Let's welcome our esteemed guests for today. The topic of the Mr. Vern Solberg, can you please come?
Yeah.
Welcome to Mr. Vern Solberg. I think you have to switch off one of the audios there. It's multiple audios are coming. Mr. Vern Solberg.
Okay.
Can you please, because it's repeating.
There's a lot of audio right now.
You have to switch off one of the audios. So can you switch off and switch on back, sir, if you don't mind? Log in back.
Audio right now.
No, you log out and log in back on the Zoom. Sir, if you don't mind, log in back.
Okay.
So I think it is better if you can log out from the Zoom and log in back. One. So till he does that, he fixes the technical thing from the Zoom and log in back. One.
You want me to log in back? You say?
Yes, sir. In today's electronics manufacturing activities, we have been seeing a consistent and very rapid growth in the data center application, and that is how the electronics manufacturing globally is increasing at an exponential growth. We have the data center. Why the data center market is growing, why I am so interested in it. Last week also I tried to talk on the data center as we had some technical glitches with Mr. Vern. But today is also I'm talking, the reason is we exchange so much of data in our day-to-day life, and every industry, every market segment, whether it can be medical, whether it can be automotive, whether it can be financial, whether it can be anything that is related in our day-to-day life, lot of data is getting transmitted. And where do you store them, right? And where do you have the transmission and the receiving technology? How do you do that? It's all done through the electronics. It's all done through the electronics board. It's all done through the electronics density, the board density, which is too high. And the chips are being designed to carry those kind of high speed receiving and transmitting technologies. And these high speed chips, high speed processor chips that we see every day, there are so many huge manufacturers out there, and they are consistently designing and developing and bringing those chips into the market. And that is how those chips act very smartly in order to transmit this data. And it is not that only the data, but it also does a lot of other activities, right? And that is where we come into the design aspect of it, and that is where we are here today to talk more on the chiplet, that is packaging challenges that we face with Mr. Vern Solberg. And let's wait for a couple of minutes. Sorry about this challenge. Sometimes technology can also give us some challenges. So welcome back to Global Electronics Friday Talk Show with your host Rajiv Kulkarni. And still, I think our guest is working on fixing the challenges on the technical glitches that he is facing right now. However, we will continue to discuss on our market trend on the data center side of it. So basically, there are so many chip manufacturers in the world, and we living in the United States, we see on a constant basis that the manufacturing of chips and the processors are really growing at a very exponential way. So I think Mr. Vern has logged in.
I am.
Okay, great. Welcome back, sir.
All
So,
right.
so, so let's start before we get into any other issues. I will start presenting the slides that we have, and here we go. Share the screen. Can you see my screen?
There we are.
Okay. So
Thank
welcome
you.
back, Mr. Vern, and let's get started. You can give a recap in 1 or 2 minutes, and then you get onto the slide if that is okay with
Well,
you.
this is where we left off. This is where the industry seems to be moving because of the economy. The polymer glass core interposers are far more less expensive to process than the silicon, and it's they build this, they make this glass in sheets that are compatible with the equipment that is already using silicon material. But right now, it looks like everybody's focusing on glass, and it took a while. There's a lot of development took place here in North America on the process of metallization and all. And then we've got at least two major glass suppliers that have already signed up to it. They get kind of referred to this as gorilla glass. It's very tough glass. It's not nearly as delicate as something you'd have over your windows. Okay. So regarding panel shape, the finished size that they're going to be supplying to the user are just slightly over 300 millimeters. And in this way, they can use the existing systems. Next slide. So polymer glass is a unique structure. Um, it To drill the holes in this material, it's a series of processes. Um, and the hole features on the die-attached side of a glass interposer have to have a pitch that in the range of 50 to 100 microns, while the terminal contact features on the bottom surface are commonly spanned out so that they would adapt to the next level of package substrate. That'd be 200 to 300 micron pitch. And you see that taper that's in the middle. They go through this initially with a very small hole with a laser, and they come back and do a chemical plasma etching process to open it up and then plate through. So it's not like a drilled hole so much as it just has a unique shape to it, but it does furnish continuity. Next. So the forming process for polymer glass is the laser introduces a kind of a modification in the glass, weakening the glass, and at a predefined areas, and that enables the increased etching rates. The process is called laser-induced deep etching. Does not create any cracks in the glass and allows precise forming of both blind and through vias, furnishing very high aspect ratios. The typical diameters are 200 to 100 microns, aspect ratios in the range of 1.4 to 110. Next. Next slide. So the interposer metallization sequence, we begin with the through glass, what they call the through glass via, initially created and filled to connect both surfaces of the glass. The glass surface is cleaned and prepared for polymer application, and that may involve surface treatments to enhance adhesion. The polymer layers applied to the glass substrate using spin coating or lamination techniques. Patterning areas are metallized, typically using sputtering or electroplating to form necessary electrical connections. And then we use photolithography or laser imaging to define the actual copper interconnect. Now, I got to say that there are now for buildup, there are actually copper coated films, and they can build it up and use a semi-additive process for building the circuit layers to do the interconnect. You could have up to three circuit layers on the surface where we're mounting components. Next. The design rules are in flux somewhat, and I have some figures here. They may change, and it depends a lot on the individual company's capabilities. So we look at the through glass via diameter. I have 20 to 30 microns per hole diameter. But a lot of companies are to be more producible. They may go to a slightly larger size if possible. As far as the via hole spacing, 600 micron conductor lines and spaces are 2 microns to 5 microns. Layer count 1 to 3. On the bottom layer is typically one routing because that's less density on the second level. Next slide, please. Next, I'll talk about high density interconnect. Now, this is the enabler, if you will. This is where the component and the glass come together, and we're not dealing with packages now. We're dealing with the bare die that has been prepared for mounting. Now, there's different techniques for mounting. There's soldering, of course, but the hybrid bonding is taking the main interest right now. Next slide. So hybrid bonding is a heterogeneous integration platform technology that enables joining of semiconductor die on wafer, die on die, and even wafer on wafer, although there's still a lot of work going on in that area. By the way, this is without solder or other additive conductive materials. This technology is increasingly being utilized for joining various semiconductor devices such as sensors, memory, and logic devices. This enables enhanced performance, increased functionality, while reducing overall package size and manufacturing cost. This example here in the corner, it's from IDEA. They're very much involved in the leading edge development of the processes, and they license the technology to others to do. And it's actually in full scale manufacturing right now, but by a lot of companies. But we don't see it because by the time it gets out to the market, it's all encased inside of the package itself. Next slide. So direct bond interconnect is they've registered that name. It is descriptive, but it allows die on die joining, ideal for vertically stacking memory. There's die on wafer, which is where most of these products will go. Die on wafer or die on panel. IDEA is the technology development licensing company in San Jose, and they've contributed a great deal in developing and adoption and implementation of hybrid bond process, and they license this technology to major foundries and IDMs. Just to make that clear, this is a very specialized technology, and it's taken a great deal of time to perfect it so that it is producible in high volume. Next slide. So the first attempt at this is what they call fusion bond. This is where the copper terminals on the die and on the substrate or interposer have a thin layer of tin plated onto the surface, and after cleaning, they bring them together. They join. It's a two-stage procedure that begins with precise alignment and pre-bonding, and then the element that's room temperature. That's followed by they stack the elements on wafers and expose it to an annealing process. It's a high temperature process, and what happens is the materials fuse together, and the tin actually becomes intermetallic with the copper. So there's really you can't see a joint there, but there is no solder, there's no flux. It's strictly a metal joining process. Next slide. Here's a cross section of that bond. Okay, see that thin area where it's the combination of copper and tin together. So it's very strong. It is very strong, but it is a high temperature process. So the next step was to move into a process that was developed by another local company in Silicon Valley, and where it's be more of a chemical induced process. Next slide. Okay, this is a low temperature hybrid direct bonding technology. Um, the process is again, it's now developed for very high volume processing, and this is a cross section that shows the two copper terminals coming together. There's no other metallization involved. It's just the copper and copper. It's a very unique process. So the bond metal is a copper nickel. Bond size in this case is 1 micron to 20 micron, and it's a low temperature process, so about 150 degrees C, and it is compatible. The compatible dielectrics are shown there. The process leverages industry standard wafer bonding equipment, enabling a high throughput, low cost of ownership fabrication process requires for high volume market applications. Next slide. So here's the step-by-step that furnished by IDEA. On the left side, you see the first step is to bring the two elements together. Let's say that the silicon item on one side, and in this case, it's showing silicon, but it could be the glass interposer on the other. And you see there's a slight air gap between the metallizations there. What initially happens is the polymer material comes together first, and then it goes through a interconnect. Actually, there's a heating process, but it's a low temperature heating where the metal actually, I know it sounds weird, but the copper grows together in this process. It stimulates the metal surfaces. Now, by the way, these surfaces have to be just cleaned. They clean it with a very controlled process, and then they bring it together, and the infusion of the two metal pads requires time and temperature, but at low temperature compared to the other processes. So anyway, it's somewhat hard to believe until you actually see the results, and it's very strong. And I might say that there's been a lot of technical papers that have been presented on the same topic. Last week I was in a IEEE meeting, and this was covered by at least 6 other companies, similar process, but all of them are basically using the IDEA process. Next slide. This is a cross section of a joint. Now, this showing an interposer on the bottom and the die on the top, and you notice I have a slightly different diameter pad or terminal, and that just helps with alignment. Now, there will be there are some companies that are actually going size on size, but the alignment of these products in high volume is very, very delicate. So I always like to have one of the pads larger than the other, so you're sure to get metal to metal interface. So this is showing the die element, the oxide bond surface, and the copper land. So pretty clear. Okay, you see the name Ziptronic, so down in the corner. That's the company that initially perfected the process, and it was purchased later by Tessera Technologies. They're a licensing company here in Silicon Valley, and they're an IDEA member company. So they're all part of under one umbrella. Next slide. Now this is from what I've learned in the meeting last week, and discussing this with the folks at IDEA. There's still a lot of area that's going to change, but if you look at the terminal pitch variations up at the top, they're looking at 10 microns down to 1 micron right now, and they're even going less. They've been in even less than 1 micron in the near future, but this is where a lot of the technology is currently. So what I've got is a terminal diameter, and that's a 5 microns in the first row there, and the land diameter is the same. But if you add tolerance for the machine and placement. We add a little more to that, and so I got 5.5 microns for the land. And then a single conductor could be 1.6 microns. If you have two conductors, they have to drop down to 1 microns each, which seems to be within the capability of the technology today. The copper conductors are formed with the semi-additive process. So they start with a seed layer of copper, and they actually plate the trace up on the copper and do a secondary etching to remove the seed layer. Next slide, please. Process challenges ahead. We're going to have smaller diameter copper terminals, and the challenge is column alignment. Deposition of the plating is another challenge. Controlling terminal coplanarity, surface roughness and hardness, temperature, time, and pressure control. The risk of intermetallic compound formation may compromise conductivity and mechanical joining. So the cleaning process, I think it's a very aggressive plasma cleaning process to make sure that there's absolutely no oxidation on the surface of the copper, and of course no particles can be tolerated. Next slide. Now here's two examples from IDEA showing the individual components on the left side mounted first to the interposer, and then the stacked memory variation could mount on top of the base interposer. Stacking die right now is these are somewhat exaggerated, but they're actually getting 16 die stacks, and it's very low profile part because they've thinned the die down to not paper thin but very thin, and it is successful. 16 high is to me it's a little to me it looks like the big challenge. 4 and 8 is more common, so it's 4, 8, and 12, but 16 is done. They're doing it. Okay. Next. Oh, by the way, they're working on stacking wafers. If you can imagine the wafer, 300 millimeter wafer, in trying to line up all of the terminals that are that's a real challenge, and I think that'll be the next generation. That's their goal, is to have a wafer stacking with glass
So
panels.
wafer stacking is what kind of thickness one, if you know, any idea?
Well, it's actually they're using pretty much the same equipment they use for wafer processing now for most of the initial work, but the equipment for alignment and all that's the area that they're in the development process. And
Wow.
how to line, they're using everything. They have to use, there's fiducials on each layer, and that all has to be
Yes.
lined up. So they have used X-ray, but I understand X-ray can damage some of the silicon, and so
Right.
they're really using optics. There's a lot going on, and they haven't allowed me back in the lab to look at it firsthand, but I know that there's a great deal going on. So the
Okay.
key advantage and benefits for the DBI process, well, significant benefits in product performance, greater interconnect density and bandwidth, energy efficient and enhanced thermal performance, improved digital signal integrity, and interconnect reliability. The hybrid bonding is a low temperature joining technology. That's the key. And so the temperature won't affect the performance of the die. Next slide. So some of the key planning issues for 2.5D and 3D packaging, that there tend to be a great deal of progress in multiple die package process refinement and system development. However, methodologies will vary a great deal. Some of the issues that will need to be resolved include selection of suitable semiconductors for multiple die packaging, establishing reliable sources of supply, the specified physical environmental operating conditions, we have to define the package design constraints and process protocols and stipulating electrical test method and post-assembly inspection. Right now, there's a whole team of people. I sat in on a SIMI meeting yesterday here in Silicon Valley, and they're talking about testing in the bonding strength and the like. And there's a great deal of standards taking place in that area. And then in IPC, they've already got a whole conference dedicated to this microelectronics packaging process coming up here in March in their what they call their expo in Anaheim, California. And they have over 120 more, or maybe 160 papers on packaging technology. So it's going to be quite an event. Next.
So what is this expo called otherwise?
Well, it's the IPC Expo. They have it every year. It's
Oh,
just that
that
this
is
year
Apex, Apex, yeah, Apex, yeah. Okay,
uh,
okay. It's the same thing.
Apex Expo. Yeah,
Apex.
it's a
Right,
two
right,
two
right, right.
names. Yeah, but anyway,
Yes.
if you check the website, it shows all of the talks, and
Yes.
I'm going to be there for the week, taking my notes and just making
Wow.
sure I am, but it just happened. I will be giving a talk there. I have a tutorial on one of the days later and my talk is mainly for printed circuit board design people to get them more
Mm,
involved because
mm,
it's definitely under their umbrella. They've been designing circuits for their whole career. It's just a matter of scaling, and they can be experts in designing the interposers. So that's my suggestion is that
mm.
they get more involved in that. So my talk
Sure.
is really focused for their benefit. Next slide.
Yeah.
So challenging days ahead. While the developers continue to explore alternative semiconductor package assembly methods, significant challenges remain. Example, new memory products have emerged with 30-micron terminal pitch and some having 2,000 I/O, and processors have entered the market already with 40,000 I/O. So it's that's the challenge. It's mind-boggling how many terminals they have. Now, a lot of the terminals are not active terminals per se. They go to power and ground, but still, that's a mass of terminals on a very small area. Next, please. Okay, just I have to mention I have a book out. This is a book that I developed for designers, and it provides the reader with step-by-step procedures in developing most cost-effective product possible. And it's available on Amazon.com or at the SMTA bookstore. Okay, next slide.
I think that's it.
Yep, that's it. That's and I there we are. And I thank you all for participating.
Yeah, and
Now,
a couple of questions here. One, if you would please, I will read that question to you. If you can answer, that's fine. If you cannot, if you have to answer later, that's also fine. I can put that in the YouTube link.
all right.
So one is about the integration. How do you ensure thermal compatibility between different chiplet materials?
That's an issue right now. The JEDEC teams have already started standardization procedures, but all they can do right now, from a general standpoint, is look at the array, what can fit within a certain area. So they've got a series of tables that they've developed, but getting uniformity from one manufacturer to the other is where the challenge will be. A lot of these commodity products could be made by two or three different companies, but they'll have to get together and work out a scheme that has the same terminal arrangement and same in and out arrangement. That we went through the same thing with chip scale products. Memory was the first that they tried to standardize on somewhat, so two or three companies could compete with one another. But there's a whole team now that they've been working on this for some time. But right now, most of the companies that are doing chiplet technology, they're they're developing in-house. They're not using the commodity market so much, but the
Okay.
commodity market wants to be part of it.
Okay. So the another question I have here is um, what are the best approaches for high speed, low latency interconnects between chiplets?
What is? What,
What are the
okay,
best
okay.
approaches? Yeah.
Oh, well, right now the coupling is very short, and if you're using copper conductors, it's probably the best conductor material, but much better than the oxides you have on the silicon base. But so I would say that I can't, I don't have the specifics on comparing, but I think with the copper conductor, they're going to have the best interface and the
Okay.
fastest interface.
Okay. Great. So what EDA tools and flows support efficient design and verification of 2.5D systems?
I
This is
can't
the
answer
last
that,
question.
but
Okay.
I would I'll have to. It's one I could bring up with some of the experts I'll be meeting with next week. Just happens we have a conference here in the San Francisco area that's
Okay.
focusing on chiplet technology. So I'll have my
Okay.
notebook out.
Okay, no worries, and that is fine.
Okay.
So I really thank you, Mr. Von Solberg, for your valuable time and sharing your expertise on this 2.5D chiplet challengings that we encounter. And I also want to mention that the presentation by Mr. Vern Solberg is the sole property of his own, company, and Global Electronics is just a platform that we bring in such a valuable, important veteran in the electronics industry who can definitely talk about various subjects, and we will bring definitely one Solberg in different another topic, but maybe in a couple of weeks maybe, and so we will let you know on those topics. So we really thank you all for watching the show, and or you will be watching the show later on, but extremely sorry for the little technical glitches that we had in the beginning. And once again, thank you very much. I think it's a very early morning for you, and thank you for participating and sharing your wealth of knowledge with all our people, with all our audience. And we will be conducting definitely more talk show with you, and sharing your wealth of knowledge to our audience out there. Thank you very much, and have a wonderful long weekend.
You're welcome.
And thank you all the people who are watching the show, and wherever you are, stay blessed and stay safe and stay healthy. Thank you all. We will see you next week with another new topic and with another new speaker. Thank you all.